So welcome back for the fourth week of the course. So in the last week we had discussed a lot about part-of-speech tagging and what are the various algorithms as such one can use to solve this problem. And we started with one particular classifier, that is HMM model for doing part-of-speech tagging. So we had gone through the basics of HMM and what are the different probabilities that one need to use to be able to come up with the best sequence given a new sentence. So what do I mean by sequence? Given a new sentence, I want to find out what are the part-of-speech tags for each of the word in the sentences. So there are many possibilities, and you need to find out what is the best probable tag sequence. So we formulated this problem as in the noisy channel model framework, and then we came up with the hidden Markov model by using certain assumptions. So in the last class, we had also discussed a bit about what we will be doing at runtime when we are given a sentence. So let me start from there, and we will see a particular algorithm on Viterbi decoding to find out the actual text sequences in a very efficient manner. And then later on I will go to the parameter learning part. So we had talked about it in the last week also, but we will devote some time over that in this week. So we had seen this figure in the last week itself. So we have this sentence, promised to back the bill, and I want to obtain the part-of-speech tag sequence for this sentence. So how do I start? I first start by finding out what are the probable part-of-speech tags for each of the individual words in this sentence. So for the word here promised, the two possible tags are VBD and VBN. Okay, it can be past tense or a participle. For the word to, there is only one part-of-speech tag possible. For the word back, there are 4 part-of-speech tags possible. We have seen that in one of the lectures. For the word the, there are 2 part-of-speech tags possible, and for the word bill, there are 2 part-of-speech tags possible. So I start by enumerating all the possibilities for each of the individual words in the sentence. Now I want to find out what is the actual part-of-speech tag sequence for this word, for this sentence. Now looking at this picture, how many different possibilities can you see? Okay, so if you start from any of the part-of-speech tag for the word promised and go to any of the part-of-speech tag for the word bill, any particular path denotes a possible tag sequence. So if you try to count the number of possibilities, okay, so it will be 2 times 1 times 4 times 2 times 2. Okay, it will be roughly 32 possible part-of-speech tag sequences. And among these 32, I have to find out what is the most probable tag sequence. Now, how should I do that? So one naive method would be that I enumerate all the possible sequences, so all the 32 sequences. I compute the probability for each sequence. So now you know how to compute the probability by using the HMM kind of model. So we did one simple example in the last class, and find out which of the tag sequence has the highest probability. That will be a naive method. You might even do that for if you have, say, only 32 or 50 possible tag sequences. But think about the sentences that might have 10 to 15 words, and some words might have 5 to 6 different tags. So you will see that it will grow exponentially. Okay, so enumerating all the sequences and computing the probabilities is not an efficient solution. So you might want to do something more efficient, so that you can find out what is the most probable tag sequence in a very efficient manner. Okay, so what should be a good algorithm? So let me take this figure, this example, to give you the intuition on what kind of algorithm would be used for finding the actual tag sequence. So to do it efficiently. Okay, so the idea here is that if you are enumerating all the 32 possibilities, you are doing some computations again and again. Okay, so can you try to reduce the time by doing it in a dynamic programming approach, where you first store computations for the smaller paths and use that for the larger paths. So we have seen one particular example of dynamic programming in the case of added distance. So we will try to use a similar concept here for decoding the actual text sequence, and this will be called Viterbi decoding. Okay. So looking at the picture, so how you can save the computation time. Okay. So let's take this sentence here. Now let me take two different paths. So one path that is there in the actual sequence, yes, VBD, TO, VB, DT and NN, and let me take another path that is VBD, TO, then JJ, then DT and then NN. Okay. So there are two paths that start with the same tag and end with the same tag. Okay. So in VBD, TO, VB, NNP, DT, NN and VBD, TO, JJ, DT, NN. Okay. So now there are two different tag sequences. Okay, and I'll want to find out probability of both of these to find out which one is better. Now, what is the idea of Viterbi decoding? The idea is that, so you are ending with the same sequence here, DT and NN. Okay, so let's look at only till that point, till DT, because after DT the computation will be the probabilities will be the same. Okay. So this is one way of saving computation. Okay, in both of these the computation after DT will be the same, so you can save on that. But what is more important here? So when you arrive at the tag DT, in one case you are coming from VB, another case you are coming from JJ. Okay, so there are two different ways you are coming to DT in these two sequences. Let us suppose that at this point, okay, I can store for the word or for the tag DT, what is the best way of arriving at DT? Is it via this path or is it via this path? So I suppose I can find out at this point what is the best way of arriving at DT. Is it this path or that path? If I can somehow find that, the later computations will, so for the two paths the later computations will be the same. Okay. So then I do not need to compute these probabilities again for the next sequence. So if I can store at this point that the best way is coming from VB and not from JJ. So when I am doing it for the next steps that are going via DT, I do not need to explore this path. So this is the idea. Suppose I write them as steps. So step 1, 2, 3, 4 and 5. At each step, for each part of speech tag, if I can store what is the best previous tag from which it should come. So which previous tag will maximize the probability of arriving at this particular tag. Then the computation are shared for the same path and I do not need to repeat the same computations again and again. So in this particular example, once I can store at step 4 for DT, the best way is coming from VB and not from JJ. When I go further, I need not worry about this path at all. I can simply continue with this path, okay? Because if this probability is P1, this is P2, the next probability will be shared. It will be times probability of NN given DT and probability of bill given NN. Okay, that will be shared across the two paths. So if I know at this point P2 is higher than P1, I can probably forget this path for going via DT. And this is the idea. This I will do for each of the step. So similarly for step 3, for each of the four part of speech tags, like for VB, I will so here it is easy, because for each part of speech tag it can come only via 2. Okay, so it is important for this case, because for DT it can come via 4 previous tags, so I need to store which of the previous tags it is coming from, which has the highest probability. Similarly for NNP, which of the 4 previous tags has the highest probability. So that is what I am going to do. At each step, for each part of speech tag, I will store what is the best probability of arriving at this part of speech tag. Okay. So let us look at the formulation. So intuition is that, so as I have explained, we are recording what is the optimal path at each state for a given step. Okay. What we are storing, what is the cheapest cost of arriving at a particular state. That means that has the highest probability, that's the cheapest cost. Now, once we have found out what are the tags at different points, we also want to write down the sequence. So I also need to store a backtrace. So this is the highest probability. So what is the particular part of speech tag that gives the highest probability? Okay, so I want to store this delta JS, that is the cheapest cost or the highest probability, to step J at step S, and also the backtrace from that state to the best predecessor. Okay, so for the previous example that we were seeing, for DT the best predecessor was VB and not JJ. Okay, so now, so this I am doing at any step S for state J. How do I use that to compute for the next step? Okay, so let us again look at it. So suppose I have stored delta J S. Okay, so here S is 3 and J is my state. It can be VB, JJ, NN and RB. So I have stored for all these 4 different part of speech tags. What is the cheapest cost of arriving at this point? What does that mean? I know at this point which path is better, VBD TO VB or VBN TO VB. Okay, so I know that for all these 4 different part of speech tags. So I store the step for this step, for this state, what is the optimal cost, or what is the most probable path. So this cost I have, or this probability I have. Now, how do I use these probabilities to compute for the next step? Say I want to compute delta J plus 1 S. How will I compute that? So now, delta JS would have taken care of the word back already. So what are the things that I added? For going from so I am sorry, here this should be step S. So this is delta J S plus 1. Okay, so this is a step S plus 1. I want to find out probability delta J. So I know the probability is at step S. Now what is the additional information? The transition from this state to this state and the emission probability of this word given this state. So I can compute it using delta J S plus 1 is delta I S times the probability of this tag sequence, that is probability of tag Tj given Ti. This is the probability of tag sequence transition, and the emission probability, that is probability of word at step s plus 1 given Tj. Okay. So this I am doing for some ith state, but there are there can be some n number of states. So I will find out the max of those. Among all the states at the previous step, I have delta S. I multiplied with it the transition probability and the emission probability at step s plus 1. Okay. And the max gives me what is the best path at this state j at step s plus 1. Okay. So now suppose out of these 4 I found out this is the best path. So I will also like to store what is the best predecessor. Okay. And this is nothing but argmax of this function. Okay. So I call that psi j s plus 1, that is argmax of the same function. Okay. And that is what I am also storing, and that's how this will continue. So what will happen at the end? I am at step 5. Okay. And I know what is the probability. So let me write down delta nn at 5 and delta vb at 5. I know both these probabilities. What is the best way of reaching at this state? What is the best probability of reaching at this state? At this point I can just take the maximum of these two, and this will give me the best probability of any possible part of speech tag sequence. And then I can use the back traceage from here to obtain the actual part of speech tag sequence. And this is my Viterbi decoding algorithm. So if we see that formally, so yes, so I am storing at each step s what is the cheapest cost, the best probability of reaching there, also the predecessor, and using that I am also computing the probabilities for the next step. Okay. That is similar to what we have seen here, the probability at the previous step, transition probabilities and the emission probability, and I take the max over all the previous possible states, also store the predecessor for the next step. And how do we end? Once we have gone through the sentence end, I will have the probabilities for all the states possible at the end, the ending word. I will take the maximum of those and backtrace from there, and that will give me the optimal text sequence for this particular sentence. Okay. So I hope this algorithm is clear. So let's take a simple example so that you can become much more familiar with that. How do you use this Viterbi decoding algorithm for any problem? So what do you see in this problem? I have a sentence. The light book. Okay. And you are given some sort of emission probabilities first, that the word the can come from the tag determiner or noun. So there are two possibilities, determiner, noun. The word light can come from noun, adjective and verb. Okay. Possibility by using Viterbi decoding algorithm. So how do we start? So I have 3 steps, 1, 2, 3. Okay. So I want to store at each step for each state. Okay. So let me call it delta 1 at step 1. Similarly, delta 2 at step 1. Okay. So what is this probability? So this will be what is the probability that the tag determiner occurs in the start of the sentence, multiply with the probability of emitting the from the tag determiner. Okay. So let us see, are these probabilities given in this question. Probability of determiner occurring in the start of the sentence. So in this question, in the last sentence, it is written, assume that all the texts that have the same probabilities to appear in the beginning of the sentence. So probabilities are given implicitly. Okay. So now the question is that how many tags would you assume? So here you can take any assumption. So in this question you are shown only 4 tags: determiner, noun, verb and adjective. So assume there are only 4 part of speech tags, and each one has equal probability of occurring at the start of the sentence. So what will the probability of determiner occurring at the start of the sentence? It will be 1 by 4. Okay. Similarly for noun, 1 by 4 times probability of the given determiner, and that is given here as 0.3. Okay. And probability of the given noun is given as 0.1. So this is your delta 21 and delta 11. So you can also further write them 0.025 and this will be 0.075. So better write them as 2.5 into 10 to the power minus 2, 7.5 into 10 to the power minus 2. Okay, so you have delta 1, 1, delta 2, 1. Now you go to the next step. Okay, so now here you want to find out delta 1, 2. In step 2, what is the best probability of reaching noun? Now noun you can reach via either here or here. Okay, so you need to compute both the possibilities and take the max over that. So let us compute these probabilities. Okay. So what will be that? So first one will be delta 1, 1 times probability of getting noun from determiner times probability of light given noun. Yes, and second one would be delta 2, 1 times probability noun given noun times probability light given noun. Okay, so let us compute these two probabilities. So you will take the max of these. Okay, so let us just compute these probabilities. So this would be so let me take it here 7.5 into 10 to the minus 2 probability of noun given determiner. So that is that we can see from the table given to us. Noun given determiner is 0.5 and light given noun is 3 into 10 to the minus 3. Okay, and this gives me 3.75 into 3, 11.25 into 10 to the minus 5. And the second one becomes 2.5 into 10 to the minus 2 times probability of n given n, this is 0.2 into probability of light given n, that will be 3 into 10 to the minus 3. Okay, and that is 0.5, 1.5, 1.5 into 10 to the minus 5. Okay, and from these two you can say that this one is higher than the next one. So this is what you will take. So you can store delta 1 2h 11.25 into 10 to the minus 5. okay, and you will also store the backtrace that is coming from this path. Okay. Same thing you will do for adjective and verb. Adjective, again there will be two possibilities coming from determiner and noun. For verb there will be two possibilities. Again you will compute the probabilities using the formula and store what is the best probability. So it will be delta 3 at step 2, delta 2 at step 2. Okay. So this is what you will store. Also you will store the backtrace. Once you have done that, now you will go to the final step. So where you will store delta 1 step 3, 1 means noun here, and delta 2 at step 3. Again you will compute that by taking all the three possibilities times the transition and all. So this will be max over 3 quantity, this will be max over 3 quantities. Again you will find out the two values, delta 1 3 and delta 2 3. And how will you actually determine the final sequence? You will take the max of this. Suppose max comes out to be this one. Then you will go to the predecessor. Okay. Suppose the predecessor was this one, you will go to here. Suppose the predecessor was this one, and so on. So you will find out this sequence, assuming this is these are the best probabilities. Okay. But I hope the idea is clear that how do you actually do this computation. So I would encourage that you complete this particular exercise on your own. Now, coming to the point of learning the parameters. So what are the parameters do we need in this hidden Markov model? So we need three different parameters. Okay. So we need the probability of starting the sentence. Okay. So that is, let me call this in the language of HMM, the pi. That is, what is the probability that a particular tag or a state starts the sequence. Okay. So I want this probability is pi I for all post tags. Okay. Then I need the probability of transition from one part of speech tag to another. Okay. So this is my transition matrix. I need all this Aij transiting from probability Tj given Ti. Yes. And I need my emission probabilities, that is probability of a word given a tag. So you can use it using a matrix B. So I need all these three probabilities to actually use this Viterbi decoding algorithm at runtime. If I do not have these probabilities, I cannot use Viterbi decoding. So now the question is, so these are my parameters of the HMM. So how do I actually find out these parameters of my HMM? So here I am saying there are two different scenarios that you might have. Okay. So first scenario is where a labeled data set is available. What do you mean by a labeled data set? You have a set of sentences available to you. For each sentence, you also know what is the actual part of speech tag sequence. So what is the part of speech tag for individual word? Somebody has manually labeled it for you. So this is a labeled data set. This is one scenario. Second scenario is you only have the corpus, but you do not have any data where the sentences are labeled with the part of speech categories. Okay. So I hope the two scenarios are clear. So scenario 1, where you have a labeled data set. And scenario 2, only corpus but no labels. So now what I am saying, for these two scenarios, you can find the parameters in different manner. So suppose you have scenario 1, you have the label data set. So what you can do for finding the parameters of HMM? So this is something we also took in the last week. So for example, you have the label data set. I want to find a parameter like the transition probability. Probability of tag j given tag I. How will you find that? In the label data set, you will have all the possible tag sequences that actually occurred in the corpus. Now from that you will find out number of times Ti and Tj occur together in the corpus, divide by number of times only Ti occurs. So this was what we said as maximum likelihood estimate. You can use that to find this probability. Same with all the other probabilities, pi I as well as p. You can find using maximum likelihood estimate. Now the problem comes when you have the corpus but no labels. Okay. So now there are no labels. So how would you actually find out probability of Tj given Ti when in the data there is no label on which word got a tag Ti or which word got a tag Tj. So you cannot compute it directly from any labels. So what is the method that you will use for learning the parameters when the corpus is available but labels are not available? And that is what we will see in the next lecture. Okay. So we will be using Baum-Welch algorithm to estimate the parameters of the hidden Markov model when the labels are not available. Okay. So this is similar to expectation maximization algorithm, and we will see what is the intuition for this algorithm and how we actually apply this. Okay. So hope in this lecture you understood how to apply Viterbi decoding when the parameters of HMM are given. Okay. And so you can do that on a new question. And in the next lecture we will discuss how do we learn the parameters when the labels are not available.